Welcome back to Math 104. Find the probability that a sample of 20 people is accurate with a margin of error of plus or minus 10%. A completely accurate poll would tell us that 40% of the public supports the law. We're allowing for an error of as much as 10% in either direction, so that if only 30% of 20 people, that means 6 people surveyed, say yes, or if as many as 50% of 20 people surveyed say yes, that's 10 people, or any number in between, then we'll say that our survey results were reasonably close to the truth. We'll say that our sample was reasonably close to representative of the entire public. We need to find the probability of 6 or 7 or 8 or 9 or 10 yes answers in 20 trials in the course of asking 20 people their opinions. It takes a bit of writing to record them all. 20 choose 6, 0.4 to the 6 times 0.6 to the 14. So this right here is the probability of exactly 6 people. That's this leftmost yellow rectangle. The probability that exactly 6 people say yes when we ask 20 people their opinion. Plus the probability that exactly 7 people say yes when we ask them their opinion. That's 0.4 to the 7, 0.6 to the 13. Plus the probability of an exactly correct sample, a perfectly representative sample, 0.4 to the 8, 0.6 to the 12. Now the probability of exactly 9 people saying yes. So 20 choose 9, 0.4 to the 9, 0.6 to the 11. And last but not least, the probability of exactly 10 people saying yes. The exponents are going to be 10 and 10. When we compute, this turns out to be approximately 0.7469. So that's quite a bit better, actually, than the answer to the corresponding question for surveying only 10 people. When we surveyed only 10 people and asked this same question, what is the probability that our sample is accurate plus or minus 10%? The probability was only 0.6665. This is quite a bit better. So surveying 20 people instead of 10 people substantially increases the likelihood that the group of people we sample will be reasonably close to representative of the whole public. When we were looking at samples that were perfectly representative of the population at large, it was more difficult to achieve that perfectly representative sample when you had 20 people rather than 10. But now we've found that if you don't ask for a perfectly representative sample, if you ask for an approximately representative sample, now it's actually easier to achieve when you have 20 people instead of 10. Here's another application of the binomial probability model. Suppose that in order for a jury of 12 people to convict the defendant, a unanimous verdict is not required. Suppose instead that at least 10 jurors must vote guilty. There are actually states in which this is the case. This is not true for federal juries, but at the state level there are states where it works this way. This means that in order for a conviction to occur, out of 12 people who are voting either guilty or not guilty, 10 or 11 or 12 of them would have to vote guilty. Suppose further that each juror's vote is independent of all the others' votes, and that each one has a 60% chance of deciding correctly whether the defendant is guilty or innocent. So we're going to regard each juror as a Bernoulli trial, with a 0.6 probability of being correct, and therefore a 0.4 probability of being incorrect. So what is the probability that a guilty defendant, a defendant who really is guilty, is convicted? In order to do that, we need to interpret this language and put our information together to figure out exactly what probability we need to compute. This is the probability that 10 or 11 or 12 jurors vote correctly. Why do I put it that way? Because we're asked about a defendant who really is guilty and the probability that the jury does convict. In order for this to happen, it must be that there are 10 or 11 or 12 votes for a guilty verdict. This is going to be 12 choose 10 times, think about it, 0.6 raised to the 10th power, and therefore times 0.4 raised to the second. This right here is the probability that exactly 10 jurors vote correctly, that is, they vote guilty, and the other 2 vote not guilty. Plus the probability of exactly 11 jurors getting it right. That's 12 choose 11, 0.6 to the 11, 0.4 to the 1, plus the probability of a unanimous verdict. Everyone gets it right. So 12 choose 12, which is just 1, times 0.6 to the 12 times 0.4 to the 0. This turns out to be approximately 0.0834. That's not very impressive. If each juror only has a 60% chance of deciding correctly about guilt or innocence, then there's a very low probability that a guilty defendant will actually be convicted. We can then ask, what is the probability that a guilty defendant is not convicted? Before we start writing things down from the binomial probability model, let's first ask, is there some nice relationship here? Are these two events complementary? That would make life much easier. Yes, they are complementary, because the guilty defendant who's there in court is either convicted or not convicted. So we don't need to write down anything complicated here. This is just a job for the complement rule. The probability here is 0.9166. Let us hope that in reality, this percentage is much higher. We follow up by asking, what is the probability that an innocent defendant is convicted? Let's think about this. In order for an innocent defendant to be convicted, that would mean that 10 or 11 or 12 members of the jury get it wrong. They vote incorrectly. I'm going to write it this way, as the probability of 10 or 11 or 12 incorrect decisions. The probability of exactly 10 incorrect decisions will be 12 choose 10 times something. So if I'm counting the number of incorrect decisions, then it's 0.4 that needs to be raised to the 10th power, and 0.6 that needs to be raised to the 2nd power. It's not so helpful to use the language of success or failure here. Or if you want to use the language of failure, you can say, okay, what's the probability of 10 failures in 12 attempts? The point is that if 0.4 is the probability of failure, then the exponent should be the number of failures. We go on to the probability of 11 members of the jury getting it wrong. That's 12 choose 11, 0.4 to the 11, 0.6 to the 1, plus 12 choose 12, 0.4 to the 12, 0.6 to the 0. That last one is the probability that they all get it wrong. Fortunately, this is quite small. It's approximately 0.0028. The flip side of the low probability of convicting someone who's guilty is the even lower probability of convicting someone who is innocent. When we ask the probability that an innocent defendant is not convicted, again, that is just the complement of the probability that such a defendant is convicted, and that is a refreshingly high 0.9972. A concluding thought here is that these computations we've been doing about juries and their accuracy have to do with real-life questions. This is important. How many people should be on a jury? Should verdicts have to be unanimous? And what are the consequences of requiring unanimity versus not requiring it? We worked with the assumption that each member of the jury has a 60% chance of correctly ascertaining whether the defendant is innocent or guilty. Is that assumption correct? What if the number is higher or lower, and what are the consequences? This is not just an exercise in a math course, these are real-life questions.